Measuring all
Okay, so today we're going to finish up with our sodium and potassium balance. When we left off, we were talking about how we balance our ions, essentially our solutes, so called our electrolytes in the body. So we were talking about sodium and the actions of our hormones that affect this, primarily aldosterone coming from our adrenal cortex. We went through a pathway which gets us to having aldosterone in our blood in the first place. So the renin-angiotensin aldosterone system. Took a look at what that looks like in the blood, and here we are. Okay, so here we're looking at the effects overall of an increase in angiotensin 2. Okay, so angiotensin 2, this part of the pathway, so right before we get to creating aldosterone from our adrenal cortex. So let's go starting there. So when your body sees an increase in angiotensin 2, so this almost the end of the pathway for our renin-angiotensin aldosterone system, we're going to have a couple effects. So for the rest of our system, angiotensin 2, it's going to get to our adrenal cortex and increase our secretion of aldosterone. So that's what we were mainly talking about on Wednesday. So we're talking about sodium. So sodium reabsorption in the distal tubules and in the collecting ducts is going to be a response to that aldosterone secretion, because the aldosterone is letting us open up channels for sodium, and we'll find out also potassium, in that apical membrane of our principal cells in these regions. So because we open up channels, and there's already a sodium gradient existing because of those sodium-potassium pumps on the basolateral membrane, sodium now has a channel to get into our cell. So it goes in one side, has that pump on the other side, so it goes out the other side. Overall, that's reabsorption because we're going from our filtrate, now essentially our urine, back into the blood. Okay? So we're reabsorbing sodium. This is going to have the effect of increasing the osmolarity of our extracellular fluid. So what we did here, right, essentially we moved a salt to the blood, to the plasma. Plasma is extracellular fluid. So that plasma now has a higher osmolarity, has more salt in it. So this actually is going to circulate around up to your brain and up to your posterior pituitary. So we're actually going to see linkage between our reabsorption of salts, our reabsorption of sodium, potassium, and our regulation of water reabsorption, because we had those osmoreceptors, right? So we had those osmoreceptors up in your brain. Okay? So we increased the fluid osmolarity. So at the posterior pituitary, this has the effect of increasing secretion of ADH, our antidiuretic hormone. So those osmoreceptors said, hey, our blood's getting salty now, we need more water. So we secreted ADH. The response to ADH secretion is then to increase water reabsorption. ADH, remember, helps us insert those aquaporin 2 molecules on the apical membrane of the cells in our late distal tubules and collecting ducts. That's the second door we needed in order to get water reabsorbed, right? We had our aquaporin 2 on the apical membrane. This is what we're inserting. So we go through, and then we can always go through the opposite side on that basolateral membrane because we always have aquaporin 3 present. Okay. So now we're reabsorbing water, and this increases our plasma volume because that water goes back into the blood. So these things are working together, this aldosterone secretion and ADH secretion, to help us increase blood pressure, or mean arterial pressure, which is why this hormone, angiotensin, appeared in some previous slides. We kind of ignored them when we were talking about our cardiovascular system. It was just a sort of additional bullet point. But now we can see how that works together, right? That angiotensin 2 is helping us create aldosterone and regulate sodium secretion, sodium reabsorption. But the reason we would want to regulate sodium reabsorption is partially so that we can also reabsorb more water along with it. Okay. Angiotensin 2 does have other direct effects. So this would be the pathway linking together all the topics we've been talking about this week. But angiotensin 2 does directly a little bit help us stimulate ADH secretion. It also actually stimulates thirst. So literally goes to your hypothalamus and makes you feel thirsty. Right? So angiotensin 2 is one of the molecules that is responsible for you feeling thirsty. When you're thirsty, you hopefully go drink some water, in which case you're going to absorb that water from your intestines, also increasing plasma volume. You're absorbing the water into your blood. So all leading back to that increase in mean arterial pressure. And another thing it's doing is acting on your arterioles themselves. So it acts on the arterioles all around your body, your systemic arterioles, right? Or differentiating those from the ones in your lungs. Its effect is vasoconstriction, right? So when we vasoconstrict, we make the radius of a blood vessel smaller, increasing its resistance, meaning we're increasing our total peripheral resistance, which increases our pressure. Okay. So all of these things together help us regulate blood pressure in response to angiotensin 2. Overall, we're raising blood pressure here, right? Right. So our effects of aldosterone, right? We need stimuli for the release of renin, which was the start of this pathway. I'm gonna just slow back, right? So the renin is coming from juxtaglomerular cells in the kidney. It's what helps us activate the angiotensinogen to angiotensin 1. Then we need endothelial cells in the capillary with these ACE receptors to convert to angiotensin 2. But we need that renin, right, to start this pathway off. Okay, so the renin is coming from these cells in our juxtaglomerular complex, right? So we have this complex, we're looking at the glomerulus, the afferent arteriole, the efferent arteriole, and here we see the ascending part of the nephron loop, right? So we're going up in that loop of Henle before we go into our distal tubule and into the collecting ducts. Okay. Okay. So in order to release renin, the things that are going to trigger that is if we have a decrease in pressure in the afferent arteriole, right? So what we're saying there, right, is if you have a decrease in pressure in the afferent arteriole, why would that be? Yeah. So you have a decrease in pressure of the blood coming here. So that's kind of a signal to us a little bit that we probably are having a drop in blood pressure. Because this blood in the afferent arteriole is just linked up to the blood everywhere else in your body. So that decrease in pressure in the afferent arteriole is kind of a signal of that. Okay. And we just saw in that big flowchart diagram that overall downstream the effects of renin, angiotensin 1, angiotensin 2, aldosterone are going to be to increase plasma volume and increase pressure. So this is a good thing to have happen in response to anything that's showing us that we had a drop in pressure. So that decreased pressure in the afferent arteriole is one of our stimuli for renin release. Sympathetic nerve activity to the kidneys is another signal here that we want to release renin, that we want to get our blood pressure back up. And other things that we can sense are decreases in the solute concentration, basically, of our distal tubule filtrate. So if we start to see low sodium and low chloride concentrations in this fluid that's coming back up, right? We got these low concentrations. That's going to be another signal for this renin release. So overall, here we have another diagram of how some of these things all link together. So if we have a drop in blood pressure, right, so a drop in MAP, so say you're hemorrhaging, right? It's going to drop blood pressure in all your arteries, all your arterioles, including the afferent arterial pressure. Okay. That afferent arterial runs right by and right through this juxtaglomerular complex. So as it goes past the juxtaglomerular cells, they release renin, which overall is helping us reabsorb sodium and therefore also downstream reabsorb more water. Okay. Other things that are happening in response to this drop in pressure, we have our baroreceptor reflex. Right, so we sense the pressure dropping in our blood vessels elsewhere in our body. In response, you have an immediate reflexive response in order to try to get that blood pressure back up in the immediate term, right? Like, so right away. And the way your body tries to do that right away is by constricting stuff with your sympathetic activity, right? So by trying to kind of modulate, kind of try to change resistance in order to change your pressure. So the way it's doing that is with increases in sympathetic activity. So when your kidney notices that your body is increasing sympathetic activity, trying to regulate blood pressure, it says, oh, great, I'll help. Right? So also release renin. So this is kind of long-term taking over for that effect. And finally, here we have how we deal with these solutes. So when you have a decrease in mean arterial pressure, this is also going to create a decrease in glomerular filtration rate. So the reason for that, right? One of our forces for glomerular filtration, so part of our glomerular filtration pressure, right, was that hydrostatic pressure in the capillaries. So if you have low pressure of the blood coming into the afferent arterial, that means you have low pressure of the blood in the glomerular capillaries, meaning you'll have a lower glomerular filtration pressure, which means you'll also have a lower glomerular filtration rate, right? Because this blood is now like kind of trickling a little more. Okay. So we have stuff just kind of trickling in, but at the same time, we're still pumping lots of ions out of that ascending loop of Henle. Right, so we drop down, we drop back up. This is the loop of Henle from our nephron loop. Our glomerulus was over here. And I guess I can draw the whole thing like this. Okay, so we had our water coming out of the descending limb. And we had active solute pumping going on in our ascending limb. Right, I'm just going to write the sodium, but other stuff too. Right, so we don't have as much filtering in because the glomerular filtration rate is low, but we still need to keep that medulla nice and salty, right? We need to keep up that osmolarity gradient in the medulla. So we still have to pump a lot of solutes out, meaning we end up with lower solutes left when we get to the distal tubules and the collecting duct. So as this passes back through that juxtaglomerular complex, the macula densa cells there sense that lower solute concentration, and they send off some little local signals. So paracrine signal secretion is just like endocrine secretion, except on a local basis rather than somewhere far out in the body. Okay. So we're increasing some local signaling here, and that local signaling ultimately also goes to the renin release. So all these three things kind of come together as a response to a drop in blood pressure. Questions about this? This is our like big picture summary. They didn't put a lot of words, but this is how it all kind of ties together. Okay. So our final, I believe, hormone for today is A&P, or atrial natriuretic peptide. So this comes from the atrial cells in your heart, right? So the atria up in the top part, right? So the cells in your atria can actually sense how distended that atrial wall is, right? So they're sensing how full the atria are getting. And they are able, therefore, to release this hormone, atrial natriuretic peptide, if they don't like what they find. Okay. So when we release A&P from the heart, this is going to increase our glomerular filtration rate. So the way it's doing that is it's going to be dilating the afferent arteriole. Okay. So afferent arteriole coming in, glomerulus, efferent arteriole going out. Okay. And the afferent arteriole and the efferent arteriole are not always the same size. And especially when we have A&P, they're not. So I'm going to write afferent, afferent, efferent. So overall, what we're trying to do here is kind of back up blood into the glomerulus and therefore increase that hydrostatic pressure in the glomerular capillary so that we force more fluid out. So to do that, we can make this blood vessel going in really big. So that's our afferent arteriole. So we dilated it, right? So we made that radius bigger, resistance lower, more blood flow here. And we're constricting that efferent arteriole, basically preventing that blood from leaving as easily. So we're creating this kind of traffic jam. So this is why we have an increase in glomerular filtration rate, because GFR is just measuring how much fluid are we getting out of the capillary. And if we have this high pressure, this blood getting kind of stuck in this capillary, we're going to have more fluid coming out. Yeah. So other things A&P do, it's going to decrease sodium reabsorption by closing sodium channels in the apical membranes. So it's basically doing the opposite of what we were looking at when we were looking at aldosterone. And the overall effect, therefore, of A&P is going to be increases in sodium excretion. So A&P is that's kind of the name of this class, right? A&P is going to increase your sodium excretion versus the aldosterone, which was increasing your sodium reabsorption. So you kind of have your kidneys working on their reabsorption of sodium and reabsorption of water, potentially fighting against your heart, which is working on this sodium excretion. Okay. Cool. So here's how that would kind of work in a diagram. So say I have a lot of blood, a lot of plasma volume, right? We've got a lot of blood, high plasma volume. That blood is circulating around. It's going to your heart. So it's going into the atria of your heart, and those atrial walls are stretching. So as your heart is filling with blood, you have more blood because you have more plasma. You're going to have more stretch on those walls, right? That's our signal for secreting A&P. So A&P is basically a response to high plasma volume. Okay. So when this circulates down to the kidneys in the blood, getting to the kidneys, it's going to overall decrease our reabsorption of sodium because it's closing those channels on the apical membrane in the distal tubule and the collecting duct, resulting in greater sodium excretion. Okay. So pretty directly, if we just follow this pathway, right, we can see that that increase in plasma volume has resulted in excreting more sodium instead of reabsorbing it. We know that water generally follows where our solutes are, right? So those big pathways with angiotensin and aldosterone all had to do with when we reabsorb more sodium, that's going to be a signal also for water to follow that sodium and have more reabsorption of water, right? So if we start excreting more sodium, that's kind of turning that signal off, right? So we can kind of start to drop down plasma volume, or at least not keep increasing it by changing that sodium excretion versus reabsorption. Okay. So the kidneys are also doing other stuff at the same time. So here, one of our ways that we knew we needed to secrete renin was we were sensing a drop in blood pressure. An increase in plasma volume would really be a rise in blood pressure. So we'd stop producing so much renin. If we don't produce renin, we're not going to produce aldosterone, which means we're not reabsorbing sodium, which means it's getting excreted out of your body. Okay. So at the same time as all this stuff is happening, our afferent arteriole and efferent arteriole are going to be changing in their radius and diameter. So we're making the afferent arteriole nice and big, we're dilating it, efferent arteriole constricting down, ultimately backing up blood into the glomerular capillary, raising that pressure, which is one of our pressures, one of our Starling forces for that glomerular filtration pressure, therefore raising our glomerular filtration rate. And now we're able to excrete more sodium because we're not slowly reabsorbing it all in the loop of Henle. We have plenty flowing past and ending up in the nerve. Okay. So aldosterone and A&P basically work in opposite directions on our sodium reabsorption, therefore also kind of on their effects on the whole system when we're thinking about like plasma volume and potentially blood pressure. All right. So our final bit about solutes is about potassium. Okay. So just like we had words for high and low sodium, we have words for high and low potassium. Okay, so emia for blood. We got a K in the middle for the potassium because potassium is K plus. Okay, and then we have our hyper or hypo. So we have our high potassium in the blood, our hyperkalemia, right? So high plasma potassium, or our low plasma potassium hypokalemia. Okay? So this is another thing you'd be able to measure. Okay? So hyper and hypokalemia could be indicators that something is going wrong with kidneys or overall with your balance of these ions in your blood, these solutes, these electrolytes, because potassium, just like sodium, is really important for our function of excitable cells, by which we mean neurons and the heart, right? All that action potential stuff was about how are we moving sodium, how are we moving potassium. If we mess with how much sodium and potassium there is in the extracellular fluid, we're going to be messing with those gradients. It's going to get bad. Okay. All right. So in your kidneys, when we're thinking about potassium ions, at the glomerulus, they're going to get freely filtered. So they're coming through with everything else that's in the plasma, ending up going from the glomerular capillaries into Bowman's capsule, into your proximal tubule, where they will then get reabsorbed, just like other stuff did. Okay? Our proximal tubule is our mass reabsorber. Okay? I'm going to go through the loop of Henle. We'll participate a little bit in that medullary osmotic gradient, but we don't need to think about measuring them so much there. When we get to the distal tubules and the collecting ducts, we are now going to see more reabsorption, but also potentially secretion. So this is one of the first times we're thinking about secretion. Okay, so reabsorption, remember, is coming. Here's my little nephron. Okay. And we're going to remember that next to our nephron, we have blood flow. Okay, so peritubular capillaries. They're doing what they're doing. Some of them go up, some of them go down. All right. So secretion is going to be when we have stuff moving from those peritubular capillaries back to our filtrate. Okay. So it's kind of the same direction as filtration, but it's not happening at the glomerulus and Bowman's capsule. So we're going from blood to the filtrate and eventually the urine, but just farther along somewhere. Okay. So in the distal tubules and the collecting ducts, sometimes we're going to have reabsorption. So sometimes we're going to go to the blood, but sometimes we're going to secrete as well. This is regulated. Okay. So, and this is regulated pretty much alongside our regulation of sodium. So our hormone for regulation of potassium, it's going to be aldosterone. So remember, aldosterone was acting on those cells in the distal tubule and the collecting duct. So I'm going to go ahead and draw one. This is my basolateral membrane. This is my apical membrane. Okay. So it was helping us increase the number of sodium potassium pumps. Right? And then a sodium potassium pump, sodium is going out, potassium is coming in. Okay. So you can start to see how it's affecting potassium as well as sodium. Right? So we're keeping the sodium environment in the cell low, but we're increasing its potassium. Okay. So the other thing that this was doing was this was opening channels on the apical membrane. So when we were talking about aldosterone's effect on sodium, we were talking about it opening up sodium channels. It is also going to help us add potassium channels. Okay. Okay. So this is going to be regulating both sodium and potassium kind of at the same time. Right. So potassium in the plasma stimulates aldosterone release and then regulates that potassium movement. Okay. So we can see here that what we've actually done, so we've pulled potassium into the cell, we opened a channel. So now we're going to release that potassium that way, potentially. So this is showing us one thing that can be happening here. So this is the reabsorption in the proximal tubule, so not what I just drew. So this is what's happening at the beginning of the nephron. Okay, so at the beginning of the nephron, we had a sodium potassium pump on the basolateral membrane. We had some unknown mechanism for getting potassium into the cell, but it does get into the cell, and then it can flow out and back to the blood. Okay, so this is not the regulated part. Okay. The regulated part is going to be secretion in the late distal tubule and collecting duct. So this is what I was just showing you with the aldosterone. Okay. So here we have that sodium potassium pump on our basolateral membrane. So our blood would be over here. Okay. We've pulled potassium into the cell, so we now have high potassium. Okay, so there's now a gradient for potassium to move out of this cell towards our distal tubule or collecting duct. And this direction is secretion because fundamentally we have moved from the blood over here all the way across the cell. All right, so here's our secretion. So this has gone the opposite direction from our sodium. So our effects of aldosterone, we were increasing the sodium reabsorption. This was coming from the adrenal cortex. We were doing that because we were increasing the number of sodium potassium pumps on the basolateral membrane. We tracked before that as it opens those sodium pumps, that means sodium can come in and then gets pumped towards the blood. Now that we're thinking about potassium, we're just tracking the opposite stuff. So those potassium channels, we still have a sodium potassium pump here. So potassium is coming into the cell. We open up a potassium channel on the apical membrane and now get out of the cell, but it's going the opposite direction from the sodium because the sodium potassium pump is moving those two things in opposite directions. So sodium and potassium are really inverse of each other for